Hi everyone. I hope I'm audible and you can share this, see the screen that I've shared. So now that we've covered the ROS projects that have been done in University of Moratuwa as well as global scope, we can start with the third session. So let's learn about a few simple theories that are important in robotics and that you undergraduates and students here can learn about and use to do some robotics projects using ROS. So the first theory that we are going to talk about is called robot locomotion. What is robot locomotion? It is the act of moving from one place to another, and it relies on the physical interaction of the robot and its environment. Here are a few examples of what robot locomotion is meaning. That is, the first two examples show leg locomotion, either with 4 legs or 2 legs, which is called bipedal. And there are further types of locomotion, such as wheel locomotion and propeller locomotion. In wheel locomotion, you can see two-wheeled motorized robot and as a track robot with tracks. And here you can see a drone and an airplane that demonstrate propeller locomotion. This is a famous example that I wanted to use to demonstrate locomotion, and many of you might recognize it because it was a famous event that happened recently. Yes, this is the Mars 2020 mission where the rover named as Perseverance was successfully landed in Mars, and even as we speak, it's collecting data and sending back to Earth. This simulation, which is available in the link that we provided, was developed by the Jet Propulsion Laboratory of NASA. And it's a great example to show how locomotion, in this case, wheeled locomotion with rocker bogie suspension, can be used to demonstrate locomotion in different terrains, such as the Mars environment. The Perseverance rover is an amazing piece of engineering. And as we discussed in the first slide, in order for a robot to enable locomotion or do locomotion, it has to interact with its physical environment. In order to do that, this robot has been outfitted with various sensors and systems that can provide it information from its surroundings. And the robot uses this information to move in the terrain of Mars, collect samples, do tests, and all kinds of things. There are amazing videos about the marvels of engineering that have been put into this Perseverance robot, and you are very welcome to check out them on YouTube. But what can we do with this concept and ROS? Here is an amazing example that was developed by the Constructism, which is an online robotics platform. And they have used ROS to develop a Curiosity Mars rover project. And here you can study about the locomotion of Curiosity rover in this environment. And there are simulations and different visualizations that you can do to understand how this works. So this is a very good example of robotics and ROS locomotion projects. Here is the project which is available in the ROS Development Studio. And we are going to introduce everyone to ROS Development Studio, an online free platform to do any kind of ROS project. And it is going to be done extensively in the hands-on session with very simple examples that all of you guys can follow. I provided the links for this project, and if you're interested in this area about astronomy and space exploration, I will welcome you guys to check this out as well. So let's start with a small area that everyone's comfortable with, wheel locomotion. And here we are going to study about differential drive, that is using two independent motorized wheels in order to provide wheeled locomotion for a robot. How do we achieve different motions with this setup? Here are 4 examples. Straight. If you want to go straight, then if both the wheels, motorized wheels, are turning in the same speed, then the robot will go straight. In order to turn left or right, you just have to adjust the speed of either wheel, and it will turn left or right. And in order to spin in the exact same position, you just need to turn the wheels in the opposite directions. So here is a nice example of how you use the locomotion to move in this sort of an arc with two-wheel independent motorized wheels. And remember this example, which I will come back to in a later slide. Now, can we do this kind of simple locomotion on ROS? Yes. And there's a nice project provided here that you can do yourself and learn about what this is about. So what we're going to go through is how we are going to develop a simple robotics platform that can accomplish two-wheeled motorized locomotion on ROS. Before we begin to do a simulation on ROS, we need to develop our robot, or in sense, we need to describe our robot in robotics or ROS platform. And to do that, as Dr. Peshala introduced, there is something called URDF, Universal Robot Description Format. And this format has been allowed to simulate all kinds of robots, from Mars rovers to copters, planes, humanoids, everything on ROS. So here is the starting point where this person has developed his robot on SolidWorks, 3D modeling software, and he has developed the caster wheel, the robot platform in blue, and 2 wheels in green. Now that he has done that, he can use certain tools which I'll introduce later to convert the robot into URDF format. So these are the URDF files. These are links. You can go and see what they look like. And once this is done, he has been able to import the files in ROS. You can see here in the SRC folder, which Dr. Peshala introduced. You can go down to URDF, and all the URDF files are here. And this is what it looks like on RBIS, which is a visualization of the robot that we just created. Now, as I mentioned in the previous slide, you can see that the robot is now performing that same action that we saw using two motorized wheels. So it's just a matter of changing the speed of either wheel in order for the robot to perform a locomotion task. So it's a very simple theory, and robotics operating system has allowed us to do a simulation of that task. Now, if you're wondering how to convert SolidWorks model to URDF, which is a pretty complex task, if you would say, there are support softwares available, such as this SW2 URDF add-on that allows us to convert to ROS easily, ROS URDF format easily. So that's just something that you can look into in this link provided. And it's not just the two-wheel locomotion task. There are other things that we can try on ROS as well. And it's up to you guys to do these kinds of new concepts and projects on ROS and learn and get the knowledge from what's out there. So here's a nice example of an obstacle avoidance robot that is it's going through an obstacle avoidance task, and this one is following this black color line while doing a locomotion task. So that's a line following robot, and both these things are quite supported on ROS, and you guys can learn about that as well. Now let's take one other theory, and it's a very important theory if you're a robotics enthusiast, and that is robot manipulator arms. What is a robot arm? We can just simply describe robot arm as machines that are programmed to execute a specific task or job quickly, efficiently, and extremely accurately. So here you can see in industrial in car manufacturing plant, and even into other situations, these robotic arms are performing tasks very efficiently and very smoothly, which even humans might not be able to do at this specified rate. Definitely a very tough situation. And a robotic arm is actually a kind of an open kinematic chain, which is a collection of links and joints. In order to study a little bit about how we can visualize robotics arms in ROS, let's cover a bit of theory on what are coordinate frames. So here is your standard Cartesian coordinate system. If there are school students, you might remember these things from A-levels or even O-levels. So in your Cartesian coordinate system, when you have three axes, you plot a point, and that point will have three coordinates called x, y, and z. So this point has three coordinates, and if you have actually two frames, Cartesian coordinate systems, and one point, then this situation can be called as having frames of reference for this point. As you can see, this blue color person and the brown color person are looking at the same dot, but they have two different frames. So those are called frames of reference. As well, you can study about some simple properties of these Cartesian coordinate systems. And the first one is you can study about translation. That is, if you move this black color Cartesian coordinate system to this blue color point, or simply move over to O dash, then that is known as a translation, a movement in a certain direction in space. And other than translation, there is this property of rotation. That is, if you turn this x to this green color location, then there's a turn by a theta degree amount, and that is known as rotation of the Cartesian coordinate system. Now that you guys are covered with a few basics of that, there is one more part to cover, and that is degrees of freedom. This is a very important area in robotics that robotic arms that you have to understand. Now, look at this simple robotic arm. It has three joints that are marked with arrows, and also three links with lengths L1, L2, and L3. Now, what a joint is if you consider, for example, a door at your home, the door is rotating about its axis of rotation. This axis of rotation is actually the hinges that are connected to your wall, the wall of the door. Now, if you consider this diagram here, this diagram in this green color bar is actually an axis of rotation, which is allowing this orange color part to rotate, for the system to rotate around this. So actually, one axis of rotation or one rotating joint is creating 1 degree of freedom. And that is what you can simply understand by looking at this diagram. So this and manipulator has 3 degrees of freedom, and we are using coordinate systems to mark the first, the second, and the third degrees of freedom using coordinates. So you can see that in red, blue, and dark light blue respectively. Now, can we do a robot arm simulation in ROS? And what would that look like? Yes, we can do one, and this is what it would look like. So this demonstration here shows a SolidWorks design similar to what we saw earlier. Now we are seeing a SolidWorks design of a robotic arm, and it has 4 turning motors. So it has 4 degrees of freedom, as you can see clearly. And here's a simulation of actually an implementation of a small 2 degrees of freedom robot done using 2 servo motors. You can see that the first servo motor is turning this arm in a 180-degree manner, and the second servo motor is also turning the small part at 180-degree manner. So those are 2 degrees of freedom, and this one has 4 degrees of freedom. And what we can do in ROS is, once we're done, we figured out with the robotic 3D model with the number of degrees of freedom that we want, then we develop the URDF model, we have covered that, and then we have to develop a ROS package to support that entire robot, and then we can go into user motion control using ROS. And we'll show that section as well. And once all those steps are done, you can see the actual robot motion in ROS. And that's a very neat step-by-step implementation of achieving any kind of robotic arm on ROS. So here you can see a combination of what we just learned, the theory that we learned together in the RViz environment. So here's a visualization of our robot that we were looking at, but now you can see that the separate coordinate axes have been placed at the respective joints. And this is a very important and very useful, I think extremely useful point of ROS, and it's called TF. So this TF framework is allowing us to see this link of transforms or coordinates, how they are linked to each other in ROS. And you can study about this more, and it is one of the fundamental things, and we'll also be explaining a little more in the fourth part of this third session. Now, it's not enough to study about simple robots, because those aren't what are used in the real world. So let's study about an industrial robot arm. And we are using this example of a KUKA robot, as you can see provided here. It's called KR210. And this robot arm has this kind of a diagram. It's showing all the dimensions and all the dynamics, the mechanics of that robot in this diagram. And what you can notice here is this gray color area, which is known as the workspace. The workspace is actually the region of a space around the robot that we can define as its operating region. And what we mean by operating region is this, there's this end of the robot called the end effector. So the region of work where the end effector of the robot is able to perform any task is known as the end effector's workspace. And this is what you can see. So it's a very cool concept, and many industrial robots have this kind of diagrams. Now we can come to a very interesting part, but we can't learn a lot about it, but we can see how ROS is used in these situations. Because in order for, this is just for information for everyone, in order for a robot to perform this kind of a very complex task, going from this red dot under this block to this green dot in this very neat and smooth manner, it's not a very simple task. There are so many different theories that are working underneath, and some of them, forward kinematics, inverse kinematics, differential kinematics, Cartesian control, and motion planning, all of them have to work together in order for this robot to work. And these are somewhat complex topics that you can learn one day when you're learning about robotics, and some of you may already know. And what we have to understand today is all of these ones can be demonstrated and analyzed and studied using ROS. That is why this platform is really wonderful. And let's look at the first example we have. This is the forward kinematics example of our KUKA KR210 robot. So here you can see that this joint 1, joint 2, joint 3, and all these joints are marked on this robot. You can see the TF tree, the transforms, and when this user is adjusting each joint, you can see that the robot is responding by moving its manipulator regions or links in space. So this change in joint translating into the robot's motors in order to change its position in space is known as forward kinematics. And that's a very wonderful concept that Ross is demonstrating to us very simply and very neatly. Now, this is a very much more advanced concept that is called inverse kinematics. And here you can see that this person is moving this pointer, this green color pointer in space. But the robot is trying to respond by following that pointer. So here it's not similar to what happened before. Here we are giving the point in space, and the robot is trying to figure out what are the joint angles the motors have to turn to in order to follow this pointer. So it's a reverse of what we studied previously, and it's called inverse kinematics. So here you can see forward kinematics provides the end effector's position, but inverse kinematics takes the end effector's position and provides the joint angles. So those are two different concepts, and ROS is absolutely amazing to study about those two. The final slide we have is for another topic that's completely different from what we studied, and that is position estimation. This is a very important part of robotics, and I'll tell you why. You can see this robot is moving in this white color line, but as it's moving forward, you can see that it's drifting from that line. So these kinds of problems are common in robotics. Just because you give the same speed to two wheels, it doesn't mean the robot will always travel in a straight path. And in order to correct the error of those kinds of situations, we need these kinds of algorithms. So position estimation is the process which calculates object position with reference to some coordinate system. And there are different kinds of filters and error correction algorithms that can be implemented on ROS, for example, the Kalman filter, to address these kinds of difficult situations. So here you can see in RQT plot, there's some kind of real-time calculation going on. And as a result of that, this robot, which is supposed to move in this irregular path, is now moving in this perfect circle. And I think Bhanuka will give a nice introduction to the application of how this is done. So I think that marks the end of my section, and I'd like to hand over to Oshada to give you guys a good overview on perception. Oshada, you can take.
Thank you, Kitme. So